Good evening everyone. I'm so sorry that I'm presenting via video. We couldn't make the travel, but please feel free to send me your questions and comments. I'm presenting an emotive lifelike robotic face called ExpressionBot developed at University of Denver. As you know, tremendous effects are required to develop robotic heads. A number of design choices must be made, such as face design and mechanic design. It's often difficult to redesign and rebuild heads based on users' feedback. An alternative approach can be using character animation technology to create 3D avatar where we can produce natural visual speech and expression and project these models onto a robotic face that can move like human head and give the animation embodiment. In this project, we developed a light projected robotic head with natural visual speech and facial expression. We can categorize robotic faces into 4 categories. Mechatronic faces will use mechatronic and electronic actuators. They have advantage of being 3D, but they look much like a stereotypical robotic face rather than human face. Examples are Kismet, developed at MIT in 2000. Android faces have larger number of actuators controlling a flexible skin. They look nicer, but they might fall into uncanny valley. They are more expensive and mechanically very complex. Examples are Albert Hugo or Zeno. On-screen avatars, on the other hand, are very low cost and flexible, but there is no physical embodiment and lack of establishing mutual eye gaze. Examples is Grace. Light projected physical avatars consist of translucent 3D masks with 2D or 3D avatar projected on them. They are highly flexible and low cost. Of course, they might also fall into uncanny valley, but because we can change the character, we can change the appearance as well. This area has been investigated since 2004 by a dome robot developed at Japan, and more advanced versions are Fairhat in 2012 or SociBot, which is commercially available. Our developed system consists of a 3-degree freedom neck system. The animation is projected by a 300 ANSI lumens projector and a fisheye lens that can save projector distance and create a compact head. The mask is also created using 3D model of the animation, and basically we have same muscle shape of the face with the animation. We also use a wig to make it more aesthetically pleasing. As I explained before, there are many light projected robotic faces, but I can say main advantage of our system comparing to existing systems is our animation. More details can be found in our paper, but generally our approach consists of 3 steps. At first, we align recorded speech using international phonetic alphabets. Having IPA in our system allows us to have other language easily later if the aligner exists. Then we group visually similar phonemes called viseme into units called viseme. For example, consonant B, P in buy, pie have the same lip shape. We categorize English phonemes into 20 viseme classes and design a 3D model for each of them in Maya. At the end, we blend them together with different weights. These weights are coming from kernel smoothing techniques and to make it more natural and smooth. There is also another important factor here. We need to close our mouths in some phonemes, such as B, P, Me, because the kernel smoothing may blend them totally with different viseme. We need to force closure for those viseme. In order to blend visual speech with emotion, a graphic artist designed 3D model of 6 basic expressions in Maya. These models are created based on facial action coding system facts. For example, joy involves cheek riser or lip puller. We then blend expression with the lip movement as this equation, where basically say that blend the current Vizime with difference of the expression and natural face multiplied by the intensity of the expression model. An important step in designing retro-projected or light-projected robotic face is the calibration. Due to projector and fisheye lens distortion, direct projection of the animation on the mask appears distorted. The calibration is done using a checkerboard on a screen and define a piecewise homography mapping between the corresponding rectangles of the mask and the screen. More details can be found in the paper. Here is the example of animation projected on the mask before and after calibration. For human-robot interaction, we evaluated our robot interacting with 23 typical adults with different age range and ethnicities. We refer the character on the screen as a screen-based agent and projection of the character on the robotic head as physical agent. Both has the same size. We evaluated the difference between a screen-based agent and physical agent in 3 different experiments. In first experiment, participants watched the robot agent and a screen-based agent in 2 different sessions randomly. A series of 6 basic emotions were displayed in random order, and the subjects were asked to select their perception. They also could select none. The result of confusion matrix on recognized expression on physical agent and the screen-based agent are shown here. As it shows, expressions joy, anger, disgust, and fear were better perceived on physical agent. In the second experiment, we evaluated the quality of visual speech and difference between the physical agent and the screen-based agent in two short segments of speech were played and 2 different lip synchronization were tested, a basic without kerneling smoothing and an approach with kernel smoothing and forced lip closure. We asked participants to rate how realistic the visual speech looked on a scale of 0 to 5, and this table shows the average rating. We performed one-tail paired t-test analysis on these data, and the results show that there is not significant preference between physical and on-screen agent, but there is a significant preference on proposed approach and over basic approach without kernel smoothing. In third experiment, we evaluated perception of eye gaze in on-screen agent versus screen-based agent. In this experiment, 5 subjects were seated around the agent in 2 separate sessions, 1 session for a screen-based and 1 session for physical agent. We performed 2 different experiments here. In one experiment, agent looked straight and only eye gaze were shifted. Participants perceived mutual eye gaze 88% of the time correctly for physical agent versus 50% of the time correctly for a screen-based agent. In the other experiment, the agent rotated its head as well and shifted its eye gaze randomly at the same time. In this setting, participants perceived mutual eye gaze 77% of the times correctly for physical agent and only 43 times for screen-based agent. Here is a video of a robotic head we developed. I hope you like it.
Hello, I am a 3-dimensional projected avatar capable of expressing emotion and speech.
To those waiting with bated breath for that favorite media catchphrase, the U-turn, I have only one thing to say. U-turn if you want to.
Goodbye. Hope you enjoy our demonstration.